Welcome back to this channel for practice problems for actuarial exams. My name is Krzysztof Ostaszewski. You can find information about me at smarturl.it/Jedi. My advice on how to pass actuarial exams is at smarturl.it/pass. This video channel is at smarturl.it/pass actuarial exams. Here you have information about online seminars and study manuals for exams P, FM, IFM, and LTAM that I offer. I direct the Actuarial program at Illinois State University. You can find information about it at smarturl.it/actuary. If you would like to offer a tax-deductible donation to support our students, please go to smarturl.it/help-ISU actuary. As you know, in life contingency exam LTAM, we study multiple lives, but it's about lives of multiple persons. It's not about multiple lives of one entity. And of course we know that cats have 9 lives, so what about those? Well, it's a different problem because in multiple lives in life contingencies, we have 2 people, and then we study the situation of a payment when the first one dies, payment when the second one dies, payment until the first one dies, payment from the time the first one dies until the second one dies, and so on. But if you have cat with 9 lives, then if you have a payment upon the last death, then the lifespan of such a cat would be from a birth to the first death, but then continues in the second life, then continues in the third life, and so on. So the lifespan is a sum of those lifespan of individual lives. So here's a problem like that. A chameleon has 3 independent lives. The force of mortality while the chameleon is within its first life is 0.1. The force of mortality while the chameleon is within its second life is 0.2. The force of mortality while the chameleon is within its third life is 0.3. The force of interest is 4% annual. A life insurance policy for which the chameleon is the insured life pays $1,000 when the chameleon ends its third life. Calculate the net single premium for this insurance for a newborn chameleon. And here's the solution. So let us write X, Y, and Z for the random lifespans of the chameleon within its first, second, and third life respectively. X is exponential with hazard rate 0.1, Y is exponential with hazard rate 0.2, and Z is exponential with hazard rate 0.3. Sorry about this typo. The lifespan for life insurance calculation is X plus Y plus Z. Let us denote it by W so that W is equal to X plus Y plus Z. First, let us determine the distribution of T equal to X plus Y. And we use the CDF technique. So F sub T of T is the probability that X plus Y is less than or equal to T, which is the probability that Y is less than or equal to minus X plus T, which is the integral from 0 to T of the probability that Y is less than or equal to minus X plus T, given that X is equal to X times F sub X of T F sub X of X dx. So basically we take the integral over the area where Y is less than or equal to minus X plus T. But X and Y are independent, so this first probability is simply the probability that Y is less than or equal to T minus X times this density, which we know to be 0.1 e to the minus 0.1 x dx. And now the probability that Y is less than or equal to T minus X is what we know from the form of the cumulative distribution function of exponential distribution with hazard rate 0.2. That's 1 minus e to the minus 0.2 times T minus X. So this whole thing is multiplied by 0.1 e to the minus 0.1 x dx. Put 0.1 in front, we have inside the integral from 0 to T of e to the minus 0.1 x minus e to the minus 0.2 T times e to the 0.1 x dx. So that's 0.1 integral from 0 to T of e to the minus 0.1 x dx minus 0.1 e to the minus 0.02 T times the integral from 0 to T of e to the 0.1 x dx. That's equal to 0.1 times a bar angle t at delta equal to 10%. minus 0.1 e to the minus 0.2 t times s bar angle t at delta equal to 10%. And that becomes, first of all, if we multiply this 0.1 times a bar or s bar, the 0.1 in the denominator cancels. So this becomes 1 minus e to the minus 0.1 t minus e to the minus 0.2 t times e to the 0.1 t minus 1. And that's equal to 1 minus 2 e to the minus 0.1 t plus e to the minus 0.2 t, or you can write this also as 1 minus e to the minus 0.1 t squared. And we take the derivative of that to get f sub t of t to be 0.2 e to the minus 0.1 t minus 0.2 times e to the minus 0.2 t. Then we figure out the cumulative distribution function of w, which is x plus y plus z, which is the same as t plus z. So this is a property that t plus z is less than or equal to w, which is the property that z is less than or equal to minus t plus w, and that's equal to the integral from 0 to w of the probability that z is less than or equal to minus t plus w, given that t is equal to t times f sub t of t dt. And then again, these random variables are independent, so this just becomes the integral from 0 to w of probability that z is less than or equal to w minus t times the PDF that we just found, 0.2 times e to the minus 0.1 t minus 0.2 times e to the minus 0.2 t dt. And then z is known to be exponential with hazard rate 0.3, so this becomes 0.2 times integral from 0 to w of 1 minus e to the minus 0.3 w minus t times e to the minus 0.1 t minus e to the minus 0.2 t dt. Okay. That's equal to 0.2 times integral from 0 to w of 1 minus e to the minus 0.3 t times e to the 0.3 t times e to the minus 0.1 t minus e to the minus 0.2 t dt. And then we multiply out the things inside. We get 0.2 integral from 0 to w of e to the minus 0.1 t minus e to the minus 0.2 t minus e to the minus 0.3 w times e to the 0.2 t plus e to the minus 0.3 w times e to the 0.1 t. Okay, well, those integrals now can be calculated, and they are either a bar or s bar. Specifically, they become 0.2 times a bar angle w at delta equal to 10% minus a bar angle w at delta equal to 0.2% minus e to the minus 0.3 w times s bar angle w at delta equal to 0.2%. At 0.2, I'm sorry, at 0.2, not 0.1%, 0.1, 0.2, so 10%, 20%, 20%, plus e to the minus 3w times s bar angle w delta equal to 0.1 or 10%. Okay, then we just write out the formulas for a bar and s bar, and then we multiply 0.2 by every single one so that it cancels out in some way every time with the denominator, and the whole thing becomes 2 minus 2 e to the minus 0.1 w minus 1 plus e to the minus 0.2 w minus e to the minus 0.1 w plus e to the minus 0.3 w plus 2 e to the minus 0.2 w minus 2 e to the minus 0.3 w. So this becomes 1 minus 3 e to the minus 0.1 w plus 3 e to the minus 0.2 w minus e to the minus 0.3 w. That's the CDF. To find the PDF, we need the derivative of this. Okay, so we take the derivative and get f sub w of w equal to 0.3 e to the minus 0.1 w. Of course, the derivative of 1 is 0. Minus 0.6 e to the minus 0.2 w plus 0.3 e to the minus 0.3 w. The net single premium is expected value of 1000 e to the minus 0.04 w. So it's 1000 times the integral from 0 to infinity of e to the minus 0.04 w times this density we just found, which is 0.3 e to the minus 0.1 w minus 0.6 e to the minus 0.2 w plus 0.3 e to the minus 0.3 w dw. Okay, then that's 1000 times the integral from 0 to plus infinity of 0.3 e to the minus 0.14 w minus 0.6 e to the minus 0.24 w plus 0.3 e to the minus 0.34 w dw. And of course, that's the same. 1000 times 0.3 is 300. 1000 times 0.6 is 600. 1000 times 0.3 is 300. And the integral of this e to the minus 0.14 WdW is just a bar angle infinity at delta equal to 14%. This is 300 times a bar angle infinity at delta equal to 14%, minus 600 a bar angle infinity at delta equal to 24%, plus 300 a bar angle infinity at delta equal to 34%. We don't need to calculate this in any way. We know this is just 1 over 0.14, 1 over 0.24, 1 over 0.34. So this is equal to 300 over 0.14 minus 600 over 0.24 plus 300 over 0.34. That's approximately 525.210084. The general formula for the probability density function of the sum x of n independent exponential distributions x1 through xn with hazard rates lambda 1 through lambda n respectively is f sub x of x is equal to the sum from I equal 1 to n of the products over j from 1 to n but j not equal to I of lambda j over lambda j minus lambda I times f sub xi of x. And you can also write this as the sum from I equal 1 to n of the products from j equal 1 to n, but j not equal to I of lambda j over lambda j minus lambda I, and the whole thing multiplied by lambda I times e to the minus lambda ix, because that's the PDF of of xi, so that's f sub xi of x. This result is nicely proved in this very interesting paper, which I'm giving you a shortcut to. And this is martyurl.it/sum of exponentials. Please remember, this is copyrighted material. This was created by me, and the solution is mine. All rights reserved. Reproduction in whole or in part without express written permission from the author is strictly prohibited.